Hello, this is section 5.6 for Calc survey, and today we'll be talking about average value. So here's just a quick example. A teacher's salary for the last 5 years, you're given 5 salaries. Find the average salary for those 5 years. So you've learned this since elementary school. You add the numbers together, divide by the number of salaries in this case, and there's the average. All right. Well, what happens if I want the average of a continuous function where you have infinitely many values? How are you supposed to add all of those values together? And then what do you divide by? So, and that's what we're going to talk about today. You need calculus to help you with that. So, in this case, so if a salary of a teacher above is represented by this function for years 6 to 10, then use your calculator to find the average salary over those 5 years using this little formula here that I'm going to explain here in a minute. So if you type this into your calculator, now we have a formula. This ends up being our average as opposed to adding those 5 salaries together and dividing by 5. Okay, so the average value of S of X from, now we used 5.5 to 10.5 because think about when we start our school year, it goes from the middle, goes from the fall to the spring, excuse me, is represented in the graph to the right. So that's what's going on here. So this is your, that should be an S of X right there. There's our function. And then we're looking between 5.5 to 10.5. Notice that the area under the curve of f of x is the same as the area under the rectangle formed by the constant line at the average value, right? So that 44,433.65, that's actually the y value. That's this horizontal line right here. And the area under that horizontal line is going to be the same as the area under this curve. And here's how I can explain that. So if you take this formula that we used up here, so if you notice that b minus a in the denominator, we're just moving that out in front of the integral. So 1 over b minus a times the integral of a to b of f of x dx. So we're just moving that b minus a over to the other side. And if you do that, you have the average value times, if we multiply over the binomial, b minus a. Well, if you look carefully, that's the y value times your base length. That's the area of a rectangle. Oh, so that's the rectangle that I'm talking about. This area is the same as the area under the curve. But if you think about it, having this set number, that y value there, what if you have a function that's all over the place and you can go up to your boss and give he or she a nice number that, okay, as long as we stay at this production level, this is our average value, we'll at least have a good way of producing enough items, since that's just a random example, okay? So it's actually a very good, useful tool to be able to find the average value. Now, the units of f of x are the same as the units of the average value of f of x. Okay. And you can kind of see that happen. Watch, remember, f of x, usually it's a rate, so maybe dollars per item, and the dx is items. So the items cancel, but then you divide by the change in items, so you end up with dollars per item again. Okay, so let's try an example. So given our function, to answer the following questions, find the average value of f of x over the interval from 0 to 2. Okay, so here we go. You're going to do 1 over 2 minus 0 times the integral from 0 to 2, and you're going to put your function in there, dx. And then you just put that in your calculator. And that's the average value. So then here's a visual. So to represent this area graphically, so I graphed our parabola. There's our parabola here. And the area from the x-axis to the curve, you get negative 22.67. Now, if I take this y value here, that negative 11.33, think of that as the height of your rectangle, times 0 to 2. That's your base length, so 2. So that's the height of the rectangle times the base length. You end up getting the exact same answer. So, isn't that cool? And it's much easier to work with a rectangle than have to deal with this weird shape. All right, so use the provided graph of f of x below to answer the following questions. So we've got our function here. So for the function f of x graphed, evaluate, so this represents the area under, we say curve, but this function here. And technically that's a piecewise function, but we're going to find the area under this function. Now I've given a problem very similar to this on quizzes, and students will stop at 1. You need to go all the way to the x-axis when you're finding the area, so be careful there. That's what this 1 times 7 is at the very beginning. That's this big rectangle here at the bottom. And then I broke it up into shapes. And that's how I'm getting the 33. So that's the area under the curve. All right. Estimate the average value of the function over 0 to 7. So take that area under the curve and divide it by 7 minus 0. That's that b minus a. And that's the average value. That's the horizontal line that I sketched right here. So the area under that horizontal line should be the same as the area under this crazy shape. So sketch the average value, we did that, and there we go. So, isn't that kind of cool? All right, another problem here. Now, this is a problem that has a lot of review in it. So, the population of a country is modeled by, there's our nice pretty exponential function, where t equals 0 is the year 2009, so we'll have to keep that in mind. Find the population in 2009 and 2019. So, we're going to plug in 0 and 10 into our function. All right. Find the average population from 2009 to 2019. So watch your notation there. So I'm going to use my new calculus technique. So 1 over b minus a times the integral from 0 to 10 of our function dt. Put this all in your calculator, and that's where we're getting, that's the average value. Now explain why the average population from 2009 to 2019 is not the average of your endpoints. Okay, so here I put this is the average of the continuous function. That's what we found here in part B. Whereas if you just took the two endpoints, added them together and divided by 2, you get a drastically different answer. Okay. So this is just the average of two numbers, whereas part B is taking the average of all of those values from endpoint to endpoint. So you're getting a much better answer with the average value. All right, is the population increasing or decreasing, and at what rate per year? Okay, so this is back, we're just reviewing now. So take that 0.78, remember that's equal to 1 plus r. A equals 1 plus r, so subtract over 1, you have a rate of negative 0.22, so decreasing 22%. What is the equivalent continuous rate? So remember, you have 8.1 e to the kt, so set that 0.78 equal to e to the k to figure out the continuous rate. So natural log both sides. Told you just some review embedded in here. Find the rate at which the population's changing per year at 2015. So this is the instantaneous rate of change. So, but remember, we're starting in 2009. So first we need to do the derivative, and this is a good review as well. So if we have a scalar here, 8.1, that stays right there. But when it's an exponential, it's natural log of the base times the original exponential, and then times the derivative of the exponent, but that's just 1. And then because we're starting in 2009, that's t equals 0, we're going to plug in 6 into our derivative to get that instantaneous rate of change. And remember, don't forget to include the units, right? And then some more review here. Find the relative rate of change, or relative rate at which the population is changing in year 2015. So remember, this was derivative divided by the function value. So that's what's going on there. And we move the decimal over, write it as a percent. And then lastly, will the rate and relative rate of change for P of t be the same or different for different values of t? So the rate's going to change in millions per year. Relative rate, however, will stay the same. And you can see that with the formula. See, when you write it all out, see how the 8.1s cancel, the 0.78 to the whatever number you put in, it's always going to cancel out. You're always going to have a consistent relative rate of change. But your slope of your tangent line along your function is definitely going to be changing, and that's what this is. Okay. So average value, you'll have to watch out for that wording. But it's basically just the area under the curve times 1 over b minus a. That's the key. And knowing that, understanding that that creates a horizontal line here, where the area under that horizontal line is the same as the area under the curve, is a really good way to make sure you have you are fully grasping the concept. Okay, but yeah, there's the formula right there. So make sure you do your homework. Let me know if you have any questions.